Okay, welcome everyone. This is the second talk of the GPU seminar series. Could you get the door, Jason? Thanks. So last time was the introductory talk. Before we get into actual GPU computing with some example code, what I'd like to do is just run through some simple algorithms and show how I would parallelize them in preparation for implementation on the GPU. This will give you hopefully sort of an understanding of how you structure your algorithms and your workflow before you actually write any code. And hopefully this will help. So I'm going to briefly review what GPU parallelism is. And then I have these five things. There's vector addition. I don't know if you can see. It's kind of faded. I have summing two vectors component-wise. I have pairwise summation, which is a special case of a bunch of other algorithms called reductions that are very useful. An example of parallel matrix multiplication, and then a couple of examples that statisticians use, like k-means clustering and a little Markov chain Monte Carlo. How many of you are from other departments, by the way, than statistics? Okay, several of you. So I'll keep that in mind when I go over the MCMC, the Markov chain Monte Carlo. All right, so just to review from last time, there's this thing called the single instruction multiple data paradigm, which is, well, SIMD for short. It's essentially when in your code you're taking the same command and applying it to multiple places in the data. So it's just this one thing that you do over and over and over again. And the classic example is something like a for loop in your code, where in this for loop I'm just taking vector B and a vector C. Both of them have a million elements, at least. And for I equals 1 to y equals 0 to a million minus 1, I am just adding the ith component of B and the ith component of C together and storing it as the ith component of A. Now, traditionally, on strictly CPU computing, without any parallelization, all these iterations run sequentially. So you would compute A1 first, and then A2 second, and then so on. If whatever's inside the for loop is really expensive, then this for loop overall can take a really long time, which is why we might do GPU computing and run, let's say, all million of these iterations simultaneously. So here we have one instance of our program running this whole loop. And in GPU computing, we spawn a million separate instances of our program called threads. And we take the ith thread, and we have that thread compute the ith element of A. So we run the program a million times, all at the same time, and have each instance of the program be responsible for a single element of A, versus having a single program run through all the elements of B and C, in sequence. And because of the architecture of a GPU, that's going to be really fast. And we can parallelize a lot more than just loops. I went over some examples last time about things that you can do to parallelize code, and applying parallelism to anywhere where you use the SIMD paradigm, there's a lot of applications. So just a review about how the CPU and the GPU work together to accomplish things like this. The CPU, you're always using a CPU no matter what. You're always using a computer with a central processing unit. And the graphics card of the GPU is hooked up to the CPU. And the relationship between the CPU and the GPU is like this. The CPU is kind of like the head administrator, the one that's really solving most of the problem. And a good algorithm will work on the CPU until there's just this single instruction set that's being applied multiple times over the same data. And the GPU would send that calculation to the device or the GPU. GPU and device are sort of interchangeable. Device is lingo for GPU. So the CPU will see that. Well, a good algorithm will take that and put that massive workflow onto the GPU where it can be executed in parallel, and then the results will be written back to the CPU. And so it's kind of like the relationship between a person and a pocket calculator. You know, you're doing a math problem. Let's say you're doing a calculus problem, and you've worked with, you know, symbols, and you've done the integral, and you found the antiderivative, and now it's time to evaluate that antiderivative at, you know, two different points, right? Which involves a lot of number crunching. And since it involves, you know, a lot of dumb number crunching, you're not gonna do that in your head. You're gonna want to plug the results into a pocket calculator and then read them off of the calculator screen. And this is kind of like how the CPU is using the GPU here. So not everything can be done strictly on the GPU, and the GPU can't operate by itself. You want to be strategic about what instruction sets you send to the GPU and read back from the GPU. And a few things to help you sort of see what you might want to send over as well. You want to send things that you can parallelize. You don't want to have print statements in your code that works on the GPU, because the GPU doesn't have access to a lot of the hardware, including, you know, the hard disk, the screen. I mean, the GPU can either be used for your display or be used for scientific computing, but not both. So you can't print to the screen, for example. You can't read off USB cards and things. The GPU is only hooked up to the CPU, is only hooked up to the rest of the computer through the CPU. So you can't really access things from the GPU directly. And you also have to think about GPU-CPU communication. In these diagrams, you see that each line represents where something communicates with something else. For example, this line is where the CPU cores communicate with on-chip memory, where they read and write back to on-chip memory. And, you know, this line represents, you know, things that are written to the GPU and read back from the GPU. And the thickness of these lines represents the bandwidth. So how much information can you send over per millisecond, for example. As you can see, there's higher memory bandwidth between, you know, the GPU cores and on-chip memory than in the CPU. So there's a really thin line here, but there's also a really thin line between the CPU itself and the GPU. So which means it's really slow to write data to the GPU and read data back from the GPU. So that's a limitation of using GPU computing in big data. It works really well, but to get that big data set over to the GPU to begin with is going to take some time. So you better be sure that the benefits of parallelizing your workflow are going to outweigh the cost of that overhead of transferring the data to the GPU and back from the GPU. Another reason why parallelism works, I should say, in this diagram is you have a lot more GPU cores than CPU cores. CPU cores only get up to, CPUs usually only have around 8, 4, or 2 cores at a time. 8's pretty high. My computer has 2. A lot of computers have 2. The Intel Core 2 Duo, which is ubiquitous, has 2 cores. Graphics cards have a lot more. Graphics cards have, I mean, they're smaller cores, but there are about 400 or 500 of them in the models that we currently have on the stat department servers. There are about 448 cores per graphics card. Any questions so far? Just a review of what I talked about last time. So that's what it looks like on the hardware level. What happens on the software level is you send instruction sets in your code from the CPU to the GPU in things called kernels. A kernel is an instruction set that is sent to the GPU and executed in parallel in separate instances of the program on the GPU. I'm going to be using the word kernel a lot, and I'm also going to be using the word thread a lot. Remember, a thread is a separate instance of your program, In this case, I mean, more specifically, threads are duplicate executions of a kernel itself. They're not duplicate executions of the whole program. Kernels are executed simultaneously in simultaneous copies, and those simultaneous copies are called threads. And these threads, for convenience, are grouped into bunches called blocks. Now, blocks are special because the threads in the same block share memory, and threads in different blocks don't. Threads in the same block can also communicate a lot more easily. And we'll see some simple examples of thread communication. I'm going to be very particular about making sure that the only threads that need to communicate with each other are ones that are inside the same block. This is very abstract at this point, but I'm going to go through some examples to clarify that. And the sum total of all threads in a kernel is called a grid. So each time I'll call a kernel, you get a grid of threads, and all the threads in the grid are divided into blocks. Now, the term grid may have come, I'm not sure about this, but may have come from the days when GPUs were used for mostly or almost exclusively graphics purposes for displays and gaming and things like that. So grid, you could think of a grid as sort of your screen, and then you would sort of divide that bitmap into different regions. I'm not sure exactly if it works that way, but it's intuitive to me, at least. So here's a toy example. So in an algorithm, you might make the GPU say to the CPU, the CPU say to the GPU, this should actually be, I meant to change this. Instead of sum two numbers, the CPU says to the GPU, sum pairs of numbers, and use the array of numbers from 1 to 8. And so some pairs of numbers would be the kernel, and the array would be the data. And one way to parallelize this calculation is to spawn 2 blocks, each with 2 threads. So I have 4 threads total, and each thread gets one of these pairwise sums, one of these summations. So I have 2 blocks, each with 2 threads. Each thread gets a pair of numbers to sum up. And instead of computing these four sums in sequence, since we have 1 per thread, they're all going to be executed at the same time. And I could have also parallelized this a little bit differently. I could have chosen 1 block, for example, and have 4 threads in that block all doing the same thing. And this would all be executed in parallel. So you're really going to have, so there are a lot of options for the number of blocks and the number of threads that you can make. And you're going to have to think about how you want to do that. And there are ways later that I'll show you to optimize that. So visually, kernels happen sequentially in time. Imagine time goes along this axis for kernels. Each kernel gets a grid. Each grid is made up of blocks, and there are multiple threads in that block. Now, I show this picture right before I go to the examples because you can have blocks in 2 dimensions and threads in 2 dimensions. It's going to be a while before I actually use that in code, but you can most of my examples, most of my example code, I'm just going to use blocks in 1 dimension, threads in 1 dimension. You can actually have up to 3 dimensions of blocks and 3 dimensions of threads. And if you're running out of blocks and threads, you're probably going to need to, because of hardware constraints, you're probably going to need to go to another dimension of blocks or another dimension of threads. All right, I've got 35 minutes. I'm going to go through the examples. So we'll start with vector addition. Pretty simple. I have 2 vectors, A and B, and I'm going to sum them up component-wise. This is sort of the for loop that I had at the very beginning. I'm going to show you some ways to parallelize that. This is more of a sanity check than everything else. It's pretty simple. One way I could do it is spawn a grid, 1 block, have 6 threads, and each thread gets a sum. Make sense? All these threads happen at once. I could also do it like this, where in my grid, I could have 6 blocks. I could have 1 thread each, and then that would accomplish the same thing. Or I could have 2 blocks, 3 threads each. Now, I'm usually not going to have something like a block with 4 threads and another block with 2 threads. I'm not usually going to have that. I sort of want to avoid that, because in your code, you're going to be able to specify for each kernel the total number of blocks and then the total number of threads per block. So each block gets the same number of threads. Some of those threads might not actually get used if, let's say, I don't know, we had a vector of length 7 and we were using 2 blocks. The closest I could come is 2 blocks each with 4 threads, and the last thread of the last block doesn't get used, which is fine. Just be aware that you can't define one block with 4 threads and another block with 3 threads, for example. And so in your code, if you want to make sure that you're not using thread indices, that are illegal or out of bounds. That'll out of bounds from, how do I want to say this? So if I had vectors like this, let's say 5 elements each, and I say, I'm going to call this program with 2 blocks and 3 threads per block, I'm going to get an extra thread, but I better make sure not to use it, because if I try to use it, I'm going to try to access the 6th element of each array, and that's an illegal reference. And you really want to make sure that you're staying within bounds. And oftentimes these errors are silent. Later, when I actually go over the code for some of these examples, I'm going to introduce a little bit about CUDA memcheck. And the MCMC example actually it showed me an error from CUDA memcheck that was related to this out of bounds memory referencing that I wouldn't have otherwise seen just by ordinary debugging and viewing output. So those errors can often be silent, those indexing out of bounds, because the things on the GPU are less verbose than things on the CPU, because things don't print to the console as easily. I just wanted to make you aware of that at this point. We'll come back to that later. Questions? Yeah?
Yeah, so did you mean that it's impossible to have a non-symmetric scenario, or that you want to avoid it?
Non-symmetric, how do you mean?
Like you could have, in this case, you might have like 4 and 2.
Yeah?
Is that impossible, or did you say you just want to avoid it?
So you can't have a block with 4 threads and another block with 2 threads. When possible, you want to, you can factor the length of your array into number of threads times number of blocks, then you should do so. That's not always going to be possible. But what's impossible is defining different numbers of threads for each block. Does that answer your question? Yeah? All right. Moving on. Let's do a more interesting example. So pairwise summation. This will be ubiquitous in really good parallel code. This pairwise summation algorithm, I use this all the time in my code. There's a built-in library called Thrust that has this actually as one of its tools. And I use that all the time. When I go over Thrust in a later lecture, I'll talk about that. And you'll see it also in one of the examples. So let's consider this vector. And let's just do this. I'm going to teach it by example. We're going to use one block of 4 threads to take the pairwise sum of this vector. So what I'm going to do is thread 0 is going to take these 2 numbers, sum them up. Next thread, these 2 numbers, sum them up. And so on for the next one. The next one takes another pair of numbers and sum them up. Notice that I have these pairwise sums, and the sum of these is going to equal the sum of these up top. So I have just reduced this problem of summing 8 things to a problem of summing 4 things. And all these threads happen simultaneously. So if in the best case scenario, computing this, all these sums only took the time of computing one ordinary sum, because all these sums happen simultaneously. Now here's the interesting part. After we take all those sums, we need to synchronize our threads, meaning that we have to wait for all the threads to finish computing these things in order to move on. Now in general, synchronization is waiting for all parallel tasks to reach some checkpoint for allowing them to continue. And it's important in this case because those values here are going to be used in the next step. And we don't want to attempt to pull some data that we haven't computed yet. So we need to synchronize all the threads. And since we need to synchronize all the threads, we want to make sure that all these threads are in the same block. You can only easily synchronize threads that are in the same block. Synchronizing threads in different blocks is very difficult and inefficient. I don't even know how to do it. So, bit of a note on synchronization. This is the sort of reason why we care about blocks. And as I said, threads from the same block can be synchronized easily, but it's difficult to synchronize threads from different blocks. Moving on. We just do the same to move on. We just do the same thing as we did before, except now we only need half the number of threads that we started with. So thread 0 computes this sum, thread 1 computes this sum. Synchronize those threads again, and then we take the last sum, and we get our answer. Now, we only needed 3 stages, which is log base 2 of the number of elements in our vector, which is 8. So we have log base 2 sequential stages. Log base 2 of 8 sequential stages. And each of those sequential stages, within each stage, things happen in parallel. Compare this to the sequential sum, where I take the sum of these 2 elements, take that with the sum, take the sum of that, sum it up with the next element, sum that up with the next element, and so on. And that's n-1 sequential steps. So if you're working in parallel code, the pairwise sum is much more efficient than the sequential sum. Log n efficiency is much better than n efficiency. So the pairwise sum is a special case of what's called a reduction. So reduction is, in general, is an operation that it's an algorithm that applies some binary operation iteratively on a vector to produce a scalar. So you could have something like the pairwise product, where we replace the product with the sum. And that's also very useful. Scans are another class of algorithms that are similar to reductions. Scans are just partial reductions. For example, a scan formally, also called a prefix sum, applies an operation on a vector that produces a sequence of partial reductions. So an example is the sequence of partial sums. So you have the pairwise sum of an entire sequence, finite sequence, and then a scan would produce the pairwise sum of each partial sequence, so the partial sum of the first 2 elements, and the partial sum of the first 3 elements, and so on. A scan would produce all of those. And these are the sorts of classes of algorithms that you'll find in the thrust library from NVIDIA, which I'll talk about later. Very useful. These are very parallelizable. My next example is matrix multiplication. So this is a bit more interesting. So let's let A be an m by n matrix, and B be an n by p matrix. And I want to compute A times B, call that C. And I'm going to use the indices I and j to denote the rows and columns of A, row elements and column elements of A. And I'm going to use j and k for the same indices, but only on B. And I'm going to make these simplifying notations here. I'm going to express A in terms of its rows, or each AI dot is just the row vector of the ith row of A. So each one of these things in A is a row. I'm going to do the same thing, a similar thing for B, but only in terms of columns, where each one of these things is a column, and each column looks like that. And this is a special case of sort of block notation for matrices. You all remember block notation from linear algebra? I'm just doing the same thing. And I do this because it's really convenient to write out. You can write out C, which is the product of A and B, just as a bunch of dot products, an array of dot products, right? So each element is the ith row of A times the jth column of B, inner product style. And I wrote it out this way because each one of these elements can be computed independently, right? So I can compute all of these dot products here simultaneously. And not only that, I don't need the threads that are responsible for computing different entries to communicate with one another. So this naturally divides the problem into an array of blocks of threads. And within each block, I can compute this dot product. Make sense? So a bit more formally, each entry C is just this sum of products of elements of A and B. And to simplify that notation, I'm going to call each of these pairwise products by this C only in triple index style. So whenever you see 3 indices, it's one of these things. If you see 2 indices, then it's the full entry of C. Formally, I assign block ik, so I'm using 2 dimensions of blocks. I'm using a row dimension and a column dimension of blocks. And I assign block ik to compute cik. And the way I do it is this block gets n threads, and the jth thread computes cijk. So you have 1 thread for each one of these pairwise products. And I synchronize the threads after I'm done, because all these pairwise products had better be computed before I move on, right? And only when I finish doing that, only when I synchronize threads, do I get to compute the sum of my cijks, which is going to be my cik. And I do that just by pairwise summing. Make sense? All right, so here's an example, really simple one. Here's A and B, and I want to compute C. And I write out C less abstractly. This is just the abstract. I'm just carrying out the abstract notation for dividing A into its rows and B into its columns, and then writing C in the corresponding way. I'm just carrying that out. So each of these is a row in A, and each of these is a column in B. And I just write out C as the array of dot products. And this is what it looks like. And I compute all of these in the exact same way, so I'm just going to focus on one of them for now. So as you can see, this is the way I divide everything into blocks. I get 9 blocks. I get 3 in each dimension. And each of these blocks can run independently of the other and simultaneously. So I'm going to focus on this block right here. So here's how the program would carry it out. So I compute this dot product here. So I take thread 0, computes 1 times 8. and thread 1 computes 2 times 3. And they're doing that simultaneously. Then I synchronize threads to make sure I have 6 and 8 computed already. And now, to finish the dot product, I need to sum these up, right? So I just do this pairwise sum where there's only one pair here in this case, since it's a simple example. I just take 8 plus 6. I get my answer. And similarly, well, I don't show the full matrix, but I do the same thing for all the other entries of Cij. Questions? Yeah.
Just a general question. So if you have threads in different blocks, then it's difficult for them to synchronize with each other, and they can't access the same memory. But is there any reason why you wouldn't want to put as many threads as possible to, minimize the number of blocks and have?
So the question is, why not have one block with as many threads as possible for those of you online? And the answer is, well, part of the answer is hardware constraints. If you run device query on one of the graphics cards, you'll see that you can actually spawn less threads per block than you can spawn blocks. I think the upper limit number of blocks is around 60,000 in each dimension. And the number of threads per block is about 1,000 in each dimension, in the first 2 dimensions and 64 in the third dimension. So you can spawn less threads per block than blocks. So you're limited there. Also, threads actually can share the same memory. I didn't talk about memory yet, but they all have access to global device memory. But I guess I wasn't clear. There's this memory higher up, closer to the cores, that's easier to access, called shared memory, that is private for each block. So, and that's a bit easier access. But they do share shared memory, and to take advantage of shared memory, you would need to use blocks. That would make your code run faster, and also allows you to have a private copy of memory for each block, and it just makes coding a little bit easier that way. That answer your question? Yeah. All right, moving on to some statistical algorithms. Actually, k-means is more computer science than statistics because it doesn't require a model. But in any case, Lloyd's k-means is very parallelizable. The idea is to cluster n points in Euclidean space, equivalently vectors, into k groups. Now remember, throughout this talk, I'm going to say that n is always a number of points, k is always a number of groups. And you would want to, here's just an example of what things might look like if you clustered them the right way. So here's how it works. I have a simpler example here. The gray squares represent points. The circles in color represent cluster centers. And here's how k-means works at its most basic implementation. So I choose initial values for cluster centers. That's not a trivial problem. I'm not going to worry about that right now, though. So imagine we've created some initial guesses for our 3 cluster centers. After we've done that, we can move on to step 2, where we assign each point to its closest center. So, for example, this square is closer to this circle than this circle, so it becomes red. And all these green points were closer to the green circle than any other circle. And we partition the points as follows. But part of the idea of this algorithm is to have these cluster centers, these circles, eventually be the group means. So this red circle should be at the mean point of all the red squares, and the green circle should be located around the center of all of the green boxes. And so we're not done, because clearly this red circle is far away from the only member of its cluster, and these green and blue circles similarly need to be adjusted. So that's what step 3 is all about. So we update the cluster centers to be the within cluster data means. And so when we do that, the green circle moves here. The red circle moves here. The green circle moves to the middle of its points. And the blue circle moves to the middle of these points. But we're still not done, because by moving the cluster means, we've changed the configuration of, we can change the distances between the points and their cluster centers, right? So now that I move this green point over here, maybe this point, which was previously closer to the blue circle, may now be closer to the green circle. So I may have to move it over to the green cluster. So I just do that back and forth until nothing changes anymore. And that's k-means. Now, repeat step 2. Yeah, this is what happens. So as you can see, when I repeated step 2, this point, this green point, was closest to the green circle. Since the red circle moved, since the red center moved, this green box is now closer to the red cluster center, so I reassign it. And similarly, other points get reassigned. And we repeat until convergence. So there's a lot of opportunities for parallelism here. So let's consider step 2 first. Step 2 was when we assign each point to its closest center. So first we have to compute the distances. For each point, I want to compute the distance to this center, the distance to this center, and the distance to this center. All those distances can be computed simultaneously for the distance from each point to each cluster center. And once I have all those distances, all these points can be assigned simultaneously. So what I might want to do if I'm parallelizing this is I spawn n blocks with k threads each. I want the number of blocks usually, because of hardware constraints, to be bigger than the number of threads per block. And I'm assuming I have more points than clusters. Obviously, I have to have more points than clusters. So I'm going to have this configuration of blocks and threads. I'm going to let thread nk compute the distance between data point n and cluster k. So I compute all those distances. I synchronize my threads so I actually have all those distances to work with. And then I let the first thread in each block assign data point n to its nearest cluster center. Make sense? So this is really 2 stages that in each individual one is parallelized. Now step 3 is recomputing cluster centers, and that also can be done in parallel. So what you do is you spawn one block for each cluster, and then within each block you compute the mean of the data in the corresponding cluster. And so each block does a pairwise sum on each dimension of, each coordinate on your points. You take the mean of those coordinates for the, in the x direction and the y direction, using pairwise summation within each block. So you do a parallelized sort of 2-dimensional or 3-dimensional version of pairwise summing to compute the mean. Make sense?
Is there any issue for synchronization?
There is in step 3. Yeah, there is, because you have to have, because in my first stage in this, I would compute the sum of all the data points. I would sum up all the, all the points in the x direction and all the points in the y direction, for example, for each of the clusters. And, well,
I think
actually,
according to the number of some particles or some points, I think there should be some difference.
there should be some difference.
Because computational time.
There will be.
Yeah.
That's unavoidable, because if you have different numbers of points in each cluster, right? Yeah, that's pretty much unavoidable in this case. But you'll have to, so you have to wait for step 3 to complete before going back to step 2, because the clusters really depend on each other across steps 2 and 3. So in that sense, yes, there is a synchronization issue. Within step 3, I mean, within step 3 itself, the synchronization issue within each block is just computing the pairwise sum. You have a bunch of synchronizations there, but yeah. Yeah, I mean, the way to avoid that problem may be in picking your initial values. So you would want to pick initial values that sort of make the clusters about the same size, and then it'll probably tend to work out better that way. That was a good point. Anything else? All right, moving on. So this is even more statistical. For you guys outside of statistics, how many of you have done or heard of Markov chain Monte Carlo? How many of you have not done it? A couple of you? All right. It takes a long time to explain in a real Bayesian statistics class. I'll do my best here. I mean, those of you who haven't done MCMC are inevitably going to be somewhat confused, but I'll try to give you at least a big picture what's going on. So, in my Bayesian statistics class, which Zeb here and I took, and Guillermo, were you there? 544 this spring? No? Okay. Well, a few of us took Dr. Jared Nemi's Bayesian statistics class, and he brought up an example with a there should be bladder cancer, not cancer bladder. I'll reverse those when I post the slides. So there's this bladder cancer data set that he pulled from cancer.gov, and it had the rates of death of bladder cancer of white males from years 2000 to 2004. And it had those data by county. So in each county, you observed some number of deaths per some number of person years due to bladder cancer. And let's define the following things before you write the model. So let y sub k be the number of deaths observed in county k. There are potentially a lot of counties depending on the size of the data set that you're looking at. In class, we looked at a subset of this data that had about what was it, 3,000 counties, something like that, around 3,000 counties. And that was just in Iowa, wasn't it? Or was it? No, Iowa doesn't have that many. Never mind. That was, yeah, 3,000 is close to the number of counties in the U.S. So, yeah, we looked at around 3,000 counties. So there are a lot of these y sub k's. And n sub k is the number of person years, and county k divided by 100,000. Person years is a it's sort of kind of a unit of time. It measures the amount of time that these deaths were observed and the number of people we observed. So roughly the number of people times the number of years that we observed each person is the total number of person years. It's an epidemiological thing. Let's define some parameters. So theta k is the expected number of deaths in 1,000 person years, 100,000 person years, sorry. And so with that in mind, we can model our data. Now to be clear, the goal here is to get some estimates of the expected number of deaths for each county. So the goal here is to take our data, our y sub k's and n sub k's, and ask, how frequently do white males die of bladder cancer in each of these counties? So we want to estimate the theta k's, and to do that, we would first specify a model where each y sub k comes from a Poisson distribution with this expectation, and all the y sub k's are independent. Now, in reality, this should actually be a spatial model where they're not independent, because counties are, the location should matter based on external factors that affect the incidence of cancer and different demographics in each county and all of that. But we're going to assume they're independent. And then we're going to define a prior on each of the theta k's. And each of the theta k's is going to have the same prior. It's going to have a gamma distribution with shape parameter alpha and rate parameter beta. I'm not using the scale parameter beta. That actually doesn't, yeah. There are two parameterizations of a gamma distribution. I'm using the rate for beta. I'm going to put hyperpriors on each of alpha and beta. I'm going to have them be uniform distributions with upper limits A naught and B naught. And A naught and B naught are going to be some constants that we fix. So strictly speaking, this is empirical Bayes because we're just picking alpha and A naught and B naught. We also assume that alpha and beta are independent in our model. So this is our model, really simple hierarchical model. And we want to sample from the joint posterior distribution because what we're really after are the thetas. But to have the thetas, we need to know something about alpha and beta. So we're going to sample these. We want to sample from the distribution of all of these together. So these have a joint distribution, and we're going to want to sample from it. Now I denote the joint distribution like this, and I'm going to break that apart. And first thing I do is just apply Bayes' rule, which gives you this. That's just Bayes' rule. Now I apply the definition of conditional probability to break up the joint prior on our parameters. And then since alpha and beta are independent, I can break up this joint prior into separate priors. And now I can say that since the y's are independent, the thetas are independent, I can break up this product and the product into a product over counties. And now since this is a Poisson distribution, I can plug in the Poisson PDF here, probability density function. This is a gamma distribution, so I plug in the gamma PDF. And these are just indicator variables that tell you, this is going to be 1 if alpha is between 0 and A naught and 0 otherwise. And these are just the PDFs of the uniform distribution. And the goal here is the technique that we're going to use is called Gibbs sampling for those of you outside the departments. And Gibbs sampling is a technique where to sample from a joint distribution, you iteratively sample from the conditional distributions. So in Gibbs sampling, we're going to iteratively sample alpha from its conditional, alpha given y, theta, and beta. Once we have our updated alpha, we're going to plug this in and sample from beta. And once we have beta, we're going to replace our previous estimate of beta with our current one and sample each theta k. Now the point of why I'm bringing this up in the first place is we can sample all the theta k's in parallel since they're independent, and we can do all these simultaneously. So we've increased. Ideally, we've increased, and in the best case, we've increased the speed of our program 3,000-fold. That's kind of speed up may not be observed in practice, but in theory, that's the best possible outcome. In any case, we do see a couple of orders of magnitude of speed up. So we got a couple minutes to see what these full conditional distributions actually are. I'm not going to go through them too quickly because I only have a couple of minutes. Let me just show you that each theta k turns out to be a gamma distribution. You can view these steps online on the slides. I don't really have time to go over them. And alpha, the conditional distribution of alpha turns out to have this form. It's really not a nice form, so we use a random walk metropolis to sample from that. That's another thing that requires its whole entire unit to teach in a statistics class. And then the betas have a nicer form, thankfully. They have the beta has a nicer form. It's a truncated gamma distribution, or it's truncated above at B naught. If we choose B naught high enough, and we can actually just use a gamma distribution to sample beta, and just not worry about this truncation, which in the implementation is what exactly Zeb decided to do. And to summarize, we get the whole Gibbs sampler. We sample theta from its full conditional by drawing the theta k's in parallel from gamma distributions. We sample alpha using a random walk metropolis once we have our thetas. And once we have theta and alpha, we sample beta again from its full conditional, which is in reality truncated gamma, but if B naught's high enough, we don't need to actually do any truncation. A little preview of what's to come. I went over some ways to parallelize algorithms. Next time, I'm going to actually go through CUDA C / CUDA C++ code. And here's sort of a workflow. You would define libraries like you would in a C program. You would define a bunch of kernels, and then you have a main function just like in C. You declare your variables. You allocate memory for things on the CPU. You also dynamically allocate memory for things on the GPU. You fill your data on the GPU in your program, on the CPU in your program. You copy that data to the device or the GPU. You execute the kernel. You write the results back. You free the memory on the GPU, and you free the CPU, and you free the memory on the GPU. And that's sort of what your code is going to look like. And so you can start to imagine how you would take these examples and write pseudocode that does this, that defines your variables, that fills the data on the, that allocates memory on the GPU and the CPU, how you would fill your data on the CPU, write it to the GPU, do your work, write back, and then compute the results, and then print the results if needed, and free everything. You can sort of think about how you might do that. For example, vector addition or pairwise sum. And I'll start to get into specifics next time about how to actually do some of that. A couple of good resources for what I talked about today. Most of the CUDA C stuff and most of this business about threads and blocks and everything, I took from this book by Sanders and Kendra. It's called CUDA by Example. It's very good and very accessible. I'm going to be relying heavily on it. And there's Dr. Nemi's Stat 544 notes. Stat 544 is Bayesian statistics, and I took the MCMC example right out of his class. And that's all for today. So the materials for the series, including a screencast of this talk, will be up online. You can already see the slides for this talk online. I'll put the screencast up as soon as I'm done. Just go to this website. Everything should be up there. Thank you for coming.